Hey guys, in this video, trying something new with this screen recording. You're not going to have to look at my hands in this video at all. So that's a good thing, I guess. But in this video, we're going to be comparing what's considered the exponential function with the logistic function. But before we look at that, let's examine something we've seen before, and that's this letter E and what it is in math. It's 2.71828 goes on. So this is actually a letter that represents a numerical value. And we see, and Euler, this mathematician, he's known to introduce this letter for this number. So it wasn't always, this number is E, he thought of it. So what it is, again, Euler did not see this, another mathematician did. But if we look at this function, 1 plus 1 over x, quantity raised to the power of x, and as we notice how what it approaches as x goes on to infinity, we see that it approaches this number, 2.71828 and so on. That someone decided to designate that value for this function, the letter E. We call it Euler's number. So I just wanted to show you that that's where this number is coming from. But let's look at, what this video is meant for. So what's so important about this letter E? It's called the natural base. It's used a lot and seen a lot in calculus and has a whole bunch of applications. But why is it called the natural base? What's interesting is we've been dealing with exponential functions, but we've seen functions where the base value can be altered. It just changes. What's interesting is that with this natural base, we can have this single base E represent any other base by simply changing this value of k. So let's say I just make my value be this 1.1. There is a value of k that will make the exponential function with the base of E equal to that. So I'm trying to, and you can see about right there. Yeah, and that's kind of amazing when you think about it. And I'm going to change it up here now, and I can find some value of k that will make this equal that function. And show you one more time. This brings us all the way up here. I can find some value of k that will make this base E function equal to it. So think about this for a moment. We can look at every exponential function and actually rewrite it with the base of E by simply finding the correct k. It's amazing. That's one reason why we call it the natural base, the natural exponential function. But often from here on, we're just going to call it the exponential function. As I'm taking this video, my hands are flying around, like I'm thinking you guys are seeing my hands or something, but it's actually a quite interesting way of taking a video, I guess I could say. So before I move on to logistic, I just wanted to say, with the exponential function, all of the ways that we've translated, reflected functions in the past, we'll see this, we can do all of that with the exponential function as well. It's just the idea that single base can represent any exponential function. And back to this. Before we move on to logistic, exponential functions we're going to consider to be unrestricted, meaning that it just continues increasing and increasing and increasing, but certain altercations that can make it continually decreasing. But it's unrestricted. It's unbound above, which in some situations, in some applications, it's not a realistic thing to use. That's when it's unrestricted. And that's where the logistic function comes in. So we've seen this before back in, I think, chapter 1, where we looked at the different types of functions. We've seen this logistic function. And we saw how it was bounded above, below. The range was 0 to 1. It was always increasing. But this function is best used for restricted growth, meaning objects or things that are growing and actually have a capacity. And we see this letter C in the function. Some sources say this is the capacity value, but others, I think our textbooks, say that this is the limit to growth. So what we see here is, as I graph this, this value C in our equation is technically going to always be our upper bound. In the logistic function, we will never pass that value that's in the numerator. So as I change this value to C, we notice that our function moves along with it. And zoom out a little bit here so you can see some more. I can go on, and my function stays within those bounds. This is used a lot when examining like the population of animals within a certain environment where food is limited. This is also used for spreading rumors around high school, because there isn't an unlimited amount of students to tell. This could be used for population growth in cities, a whole bunch of applications in biology, social sciences, and whatnot. So this value A in the equation is simply going to change the y-intercept of our equation. But by default, the y-intercept is 1. Actually, no, that's not true. It's not 1. But it changes the y-intercept of our function, our initial value. So that's the logistic function. The main thing is we have this carrying capacity, this limit to growth, where our function can never get past it, and it's going to be quite visible to us in the equation. It's just the numerator. And I do want to say, before looking at the example, you might be wondering if there's any way to make an exponential function with base e, to translate it, reflect it into this logistic function. It's actually not possible to transform an exponential function to make it logistic. Just a big difference between the two, other than the appearance, is one is unrestricted, unlimited growth, whereas this one here is restricted. Okay, so we've looked at logistic functions. So what's really interesting is how these functions can be seen in application. So this situation I pulled from our textbook. It talks about the population growth in Dallas, Texas since 1900. So I'm just assuming that these values are right. So in 1900, apparently, or this is currently, they figured out that the carrying capacity in Dallas, Texas is 1,301,642. That's the carrying capacity. Now, we know that because that's our numerator, but the other values, they alter the initial value, they alter the rate at which the population is approaching the carrying capacity. But here's our situation. According to this model, when will the population in Dallas, Texas reach 1 million? So if I plot these two, and I'm plotting them because we do not, at this moment, know of any algebraic way of solving this situation, so we're going to have to use a graph. So I plotted our population function, I plotted y equals 1 million, and our intersection is going to yield for us the solution. So interpreting what this says, 84.513 comma 1 million. So since 1900, we would interpret this answer as in 1984 and a half, 1984, the population of Dallas, Texas reaches 1 million. So we could argue that what is it? So that would be 2053. In 2053, we are extremely close to reaching Dallas's carrying capacity. But there's a lot we can do with this graph. We can look at, where were we at the beginning? It's just a lot of things that we can do with logistic functions and examining the population's growth. Okay, so you're going to come into class, and we're going to actually look at a couple of these situations, more of logistic, and then we're actually going to try a rumor experiment, just to see how that can be related to a logistic function. Okay, so any questions or comments? I know this is a very different video, but any questions or comments you have, please post them in the classroom, and I will see you later on.